Hello everyone. In this video, we will learn about the concepts of direct central impact and oblique central impact. We will also learn to apply the conservation of momentum principle and coefficient of restitution in solving impact problems. Impact occurs when two bodies collide with each other during a very short period of time, causing relatively large forces to be exerted between the bodies. A very good example of impact is the striking of hammer on a nail. Central impact occurs when the direction of motion of the mass centers of the two colliding particles is along a line passing through the mass centers of the particles. This line is called the line of impact. The line of impact is perpendicular to the plane of contact. The plane of contact is a plane that is tangent to the surfaces of the colliding particles in contact. If the velocities of the two particles are directed along the line of impact, the impact is said to be a direct impact. The example shown here is an example of a direct central impact where the velocities of particles A and B, VA and VB, are directed along the line of impact. If either or both particles have velocities directed along a line other than the line of impact, then the impact is said to be an oblique impact. For example, in this case, the velocities of particles A and B, VA and VB, have directions other than the line of impact. Now let us look at direct central impact. Every impact has three stages. The first stage is before the impact. Consider two particles A and B with mass MA and MB that are moving in the same straight line and to the right with known velocities VA and VB. If the velocity of particle A VA is larger than the velocity of particle B VB, then particle A will eventually strike particle B. The second stage in impact is the period of maximum deformation. Under the impact, the two particles will deform, and at the end of the period of deformation, they will have the same velocity u. The third stage, which is after the impact, is the period of restitution. At the end of this period, depending upon the magnitude of the impact forces and upon the materials involved, the two particles will either have regained their original shape or will stay permanently deformed. The particles will travel with velocities VA prime and VB prime at the end of the period of restitution. Now, if we consider the two particles as a single system, we'll note that there are no external impulsive forces acting on the system of particles. Therefore, the total linear momentum of the two particles is conserved along the direction of motion, and hence we can write MAVA plus MBVB is equal to MAVA prime plus MBVB prime. Now, if our goal is to calculate the final velocities VA prime and VB prime, then the conservation of momentum equation only is not enough. It is necessary to establish a second relation between the velocities VA prime and VB prime. This will be discussed in the next slide. Now let us analyze the motion of particle A. During the period of deformation, if we apply the principle of impulse and momentum to particle A, Since the only impulsive force acting on A during this period is the force P exerted by particle B, we can write MAVA, the initial linear momentum of particle A, minus integral P dt, which is the deformation impulse, is equal to MAU, the final linear momentum of particle A during the deformation time period. Now let us consider the motion of particle A during the period of restitution. If we denote the force exerted by B on A during this period by R, then from the principle of impulse and momentum we can write MAU, the initial linear momentum of the particle during the restitution phase, minus integral R dt, which is the restitution impulse, is equal to MAVA prime, the final linear momentum of particle A during the restitution phase. In general, the force R exerted on A during the period of restitution differs from the force P exerted during the period of deformation, and the magnitude of the restitution impulse integral R dt is smaller than the magnitude of the deformation impulse integral P dt. The ratio of the magnitude of the restitution impulse to the magnitude of the deformation impulse is called the coefficient of restitution. It is denoted by the letter E. Therefore, E is equal to integral R dt over integral P dt. The value of the coefficient of restitution E is always between 0 and 1. It depends on a large extent on the two materials involved, and it also varies considerably with the impact velocity and the shape and size of the two colliding bodies. From the equations of impulse and momentum during the deformation and restitution phase, we can also write down that E is equal to U minus VA prime over VA minus U. If we do a similar analysis on particle B, then we'll get the coefficient of restitution E to be as VB prime minus U over U minus VB. If we equate the two coefficient of restitution values for particles A and B, then for both particles we get coefficient of restitution E is equal to VB prime minus VA prime over VA minus VB. In other words, the coefficient of restitution is the ratio of the relative velocities of the two particles after impact to the relative velocity of the two particles before impact. There are two limiting cases for direct central impact. When the coefficient of restitution E equals 1, then the impact is called a perfectly elastic impact. In perfectly elastic impact, the relative velocities of the particles before and after the impact are equal. In perfectly elastic impact, the total energy as well as the total momentum of the particles remain conserved. When the coefficient of restitution E equals 0, the impact is called perfectly plastic impact. There is no period of restitution, and both particles stay together after the impact and travel with same velocity. In perfectly plastic impact, the total momentum of the particles remain conserved. Therefore, to summarize, in direct central impact, the conservation of momentum principle applies to the system of particles. Therefore, summation MIVI, which is the total linear momentum of the system of particles before the impact, is equal to summation MIVI prime, which is the total linear momentum of the system of particles after the impact. The coefficient of restitution relates the relative velocities of the particles before and after the impact. E, the coefficient of restitution, is equal to Vb prime minus Va prime, which is the relative velocity of the particles after impact, over Va minus Vb, which is the relative velocity of the particles before the impact. For perfectly plastic impact, the coefficient of restitution E is equal to 0. The particles stick together and travel with the same velocity after the impact. Therefore, V prime B is equal to V prime A is equal to V prime, which is the final velocity of the particles. And the momentum conservation equation takes the form MAVA plus MBVB is equal to MA plus MBV prime. For perfectly plastic impact, the total momentum of the particles is conserved. For perfectly elastic impact, the coefficient of restitution E is equal to 1. The relative velocity of the particles after the impact, Vb prime minus Va prime, is equal to the relative velocity of the particles before the impact, Va minus Vb. For perfectly elastic impact, the total momentum and total energy of the particles is conserved. Now let us look at oblique central impact. When the velocities of two colliding particles are not directed along the line of impact, it is called oblique central impact. Recall that the line of impact is the line joining the mass centers of the colliding particles. Therefore, this is our line of impact. The common tangent, which is perpendicular to the line of impact, is called the plane of contact. We choose our coordinate axis, such as our n-axis or our normal axis is directed along the line of impact, and our tangential axis or t-axis is directed along our plane of contact. Now from the impulse and momentum diagram, we see that MAVA and MBVB are the initial momentums of the particles before impact. F delta t and minus F delta t are the internal impulses acting on the particle along the n-axis during the impact, and MAVA prime and MBVB prime are the final momentum of the particles after impact. Now, if we look at each individual particle, we'll note that there are no external forces acting on each individual particle along the t-axis. Therefore, there is no tangential impulse component, and the tangential component of momentum for each individual particle is conserved. Therefore, we can also say that the tangential component of the velocity of each particle remains unchanged. Hence, VAT is equal to VA prime t and VBT is equal to VB prime t. Now, if we look at the system of particles, we'll note that there are no external forces acting on the system of particles along the n direction. The internal impulses acting on the two particles along the n direction are equal and opposite to each other. Therefore, the total momentum of the system of particles along the normal direction or along the n direction is conserved. Hence, MAVAN plus MBVBN is equal to MAVA prime n plus MBVB prime n. Also, in oblique central impact, the normal components of the relative velocities of the particles before and after the impact can be related by the coefficient of restitution. Therefore, VB prime n minus VA prime n, which indicates the relative velocities of the particles along the n direction after the impact, is equal to E, which is the coefficient of restitution, times VAN minus VBN, which indicates the relative velocity of the particles before the impact along the n direction. Now let us look at a special case of oblique impact called the constrained oblique impact. In the constrained oblique impact, one or both of the colliding particles is constrained in its motion. Consider, for example, the collision between the block A and the ball B. The block A is constrained to move on a horizontal surface and the ball B is free to move in the plane of the figure. Let the t-axis denote the plane of contact between the block A and ball B, and the n-axis denote the line of impact between the block A and ball B. If we assume that there is no friction between the block and the ball or in between the block and the horizontal surface, then we note that the impulses exerted on the system consists of the impulse of the internal forces F and minus F, which are directed along the line of impact, which is the n-axis, and the impulse of the external force F external, which is exerted by the horizontal surface on the block A, and it is directed along the vertical y-axis. Let VA and VB be the initial velocities of the block A and ball B, and VA prime and VB prime be the final velocities of the block A and ball B after the impact. Here, the tangential momentum of the ball is conserved because there are no impulses acting on the ball along the tangential direction. Hence, the tangential component of the velocity of the ball B remains unchanged. Therefore, VBT is equal to VB prime T. Note that the tangential momentum of the block is not conserved here because the external force F external exerted by the horizontal surface on the block A has a component along the tangential direction or the t-axis. The total momentum of the ball and the block is conserved along the horizontal axis. Since there are no external impulses acting on the block and the ball along the x-axis. Therefore, we can write MAVA plus MBVBX is equal to MAVA prime plus MBVB prime x. Also, the normal components of the relative velocities of the ball and the block before and after the impact are related by the coefficient of restitution. Therefore, we can write VB prime n minus VA prime n is equal to E, which is the coefficient of restitution, times VAN minus VBN. Now let us look at an example problem here. In this example problem, it is mentioned that a ball is thrown against a frictionless vertical wall, and immediately after the ball strikes the wall, it has a velocity of magnitude v and it forms an angle of 30 degrees with the horizontal. The coefficient of restitution E between the ball and the wall is given to be as 0.90, and we are asked to determine the magnitude and direction of the velocity of the ball as it rebounds from the wall. We are to assume that the wall has infinite mass so that the wall velocity before and after impact is 0. Our strategy to solve this problem would be to first establish our line of impact, which is our n-axis or the normal axis, and the plane of contact, which is our t-axis or the tangential axis. We will then resolve the velocity of the ball into the normal and tangential components. Since the problem is that of an oblique central impact, we will apply the conditions of oblique central impact in solving for the velocity of the ball. We first begin by establishing our n and t axis. Now note when the ball strikes the wall, the t-axis is the common tangent between the ball and the surface of the wall. Therefore, our t-axis is along the surface of the wall. So that's our t-axis. And our n-axis is perpendicular to the t-axis. So our n-axis is perpendicular to the surface of the wall. Next, let's look at the conditions which are given in the problem. So let's first look at the ball. The initial velocity of the ball is given to be as v. So if we find out the normal and tangential components of the velocity of the ball, Vn will be v cos 30 and Vt will be v sin 30. Now let Vn prime and Vt prime be the final components of the velocity of the ball in the n and t direction, and let mb be the mass of the ball. Now for the wall, let Vw be the velocity of the wall, the initial velocity of the wall, which is 0, and Vw prime be the final velocity of the wall, which is also 0. Now since the velocity of the ball is 0, we have no components of the velocity of the wall. Let mw be the mass of the wall, and from the problem this is infinite, and the coefficient of restitution is given, which is 0.90. The next step would be to apply the conditions of oblique central impact. If you recall, the conditions of oblique central impact are: the first condition is along the t-axis, the individual momentum remains conserved. Individual momentum is conserved. Along the n-axis, the system momentum is conserved. And also along the n-axis, the coefficient of restitution relates the relative velocities after and before impact. So we can work with 3 sets of equations when we are solving problems for oblique central impact. Now note, in this problem, we are given that the wall has an infinite mass. Therefore, the system momentum conservation equation cannot be written along the n direction, and the momentum conservation equation becomes invalid. Therefore, we only work with equation 1 and equation 3 in this problem. So now if we apply the condition 1, which is the individual momentum is conserved. So if we apply this for the ball, then from 1 we can write mb vt is equal to mb vt prime. mb cancels out, therefore we can write vt prime is equal to vt, and vt is v sin 30, or we can write vt prime is equal to 0.5 v. Now let's apply this third condition, which is the coefficient of restitution E relates the relative velocity after impact and the relative velocity before impact. So E is equal to the relative velocity of the ball and the wall after impact divided by relative velocity of the ball and the wall before impact. So for the after impact, the relative velocity would be Vw prime minus Vn, and note that this condition applies only along the n-axis. Therefore, Vw prime minus Vn prime is divided by Vn minus Vw. These two are 0. So therefore the E is equal to minus Vn prime over Vn. The value of E is given to be as 0.90. Therefore this implies that 0.9 is equal to minus Vn prime, which is unknown, over Vn is V cos 30. This gives us Vn prime is equal to minus 0.9 times V cos 30. Cos 30 is 0.866 times V. This is equal to negative 0.7794 V. Therefore, the magnitude of the final velocity of the ball V prime would be equal to square root of Vn prime square plus Vt prime square. So note we already calculated this. Vn prime was negative 0.7794 times V, this square, plus Vt prime was calculated to be as 0.5 V, so 0.5 V square. This gives our V prime to be as 0.926 V. So that's our answer. Now the direction of the final velocity of the ball would be equal to theta is equal to tan inverse Vt prime over Vn prime. This is equal to tan inverse Vt prime is 0.5 V divided by Vn prime is negative 0.7794 V. This gives our theta to be as 32.7 degrees, and this angle is with respect to the negative x-axis. Thank you for watching the video.